So last time we discussed an example about sampling, creating a sample space to calculate the probability of an event happening. So we took a permutation of 5 different gaining controllers and took the permutation of that 1 divided by that. So we got our probability. This time, let's say we want to estimate. A lot of the stuff that we're covering, especially in week 2, has to do with medical data. We talked about sepsis, that was the discussion. AI is a very important field within healthcare, and some of you may already be in healthcare or planning on going in healthcare. I'm definitely a data evangelist myself, and I also believe in data science, clinical data science, and AI applications in healthcare, but that may not necessarily be your chosen industry. But we're going to go ahead and use this as an example to showcase what we can do with respect to wait times in the hospital, especially in the emergency room. So let's say that the average wait time, or let's assume that there's a normal distribution, because we like to begin, remember, everything with the assumption that the data is going to fall under a normal distribution. And then over time, you're going to find that data drifts. It's not always going to behave the same way. So it's really for you to set up a hypothesis testing framework to establish whether or not the data has changed over time t. And so assuming that it's a normal distribution, we can say that the average wait time is 120 minutes. I'm just going to write this down freehand for now and maybe make this into a markdown cell. I was thinking about writing it with a pen, but that's kind of a waste of time. The standard deviation, on the other hand, is, we're just setting some random numbers here. It's about 20 minutes. May not be realistic. And let's say we want to take a random sample of n equals 30, because remember, again, 30 is a very important number. It's based upon the central limit theorem. And we want to use those number of patients to sample, to estimate that average wait time, whatever it is. Then we have the mean and the standard deviation and so on and so forth. So we can illustrate this difference between the sample data distribution and the sampling distribution of the mean using Python. And so what we're trying to do is get the sampling distribution y, and that's based on what would happen if you took many repetitive samples of n. And in this case, we have 30, and then we calculate the sample mean for each of these. So we've already imported pandas. We might want to plot this, so we'll see if we need to import a plotting library at the end of the day. One important thing, and I can't stress this enough, whenever you're trying to reproduce or simulate something, it's very important to set a random seed. And in Python, unless you're working with scikit-learn, it's not random underscore state, it's random dot seed. So let's set it to 0, just a standard random seed. That way, if we run it again and again and again, we'll keep getting the same results. And then from there, we need to set up the parameters for the population distribution. So we have the mean wait time in minutes and also the standard deviation sigma. So we have from above mean, where mu is equal to 120, and our standard deviation sigma is equal to 20. Let's go ahead and run that. Let's run the first cell as well so we can activate our libraries. Okay. And then, of course, we also have n is equal to 30. Let's run that again. And let's say that we also want the number of samples for our sampling distribution. Let's say we'll give them 1,000 samples. So number of samples is equal to 1,000, like so. We'll run that again. And so if we want to generate a single random sample from this sample distribution, we can calculate that by using the random dot normal function And that takes in 2 arguments. If you look at the documentation, what we've already assigned to mu and sigma, actually 3 arguments, as well as n. So when we run that, this will be our single sample. Let's go ahead and actually print that as well. Single sample. I know we talked about printing with F strings last time, but we don't always have to. We can just do something like this. Here we go. So this is our single sample. And so if we want to generate multiple samples so we can create the sampling distribution of y, or what we're trying to predict, if you want to be precise, y hat, then for that we set up a new variable called sample underscore means, and that is equal to, again, I'm going to do a list comprehension here, but you don't have to do it this way. There's an easier way to do it, but I encourage you to learn how to work with list comprehensions. So in this particular case, we're going to nest it in a pair of brackets. We're going to just take the simple mean using the NumPy mean function to get the sample mean of what we've defined above from np.random.normal, mu, sigma, and all that. Inside that function, just copy it over. And all we're saying here now is this is for in the range of number of samples, like that. So when we run that, we should also be able to get those sample means like so. Just change the print statement here. There we go. So these are our sample means. But I think it would be nice if we illustrated this using graph. And so for that, we should indeed import matplotlib.pyplot. Showed you how to do this last time as PLT. It's pretty basic. And then we're going to create a plt.hist to get the distribution of what? The single sample. And let's see what happens if we do it this way. Okay, let's clean it up. Let's change our edge color to black so we can see those bars pop out. Oh, and that's a string, always. So that cleans it up. And then we can also, right now the default number of bins is 10. But let's see what happens if we change it to 15. To actually also get the length of this 30. So that makes sense to put this into a bin size of 15. And of course, as always, remember to label your title, your x-axis label, as well as your y-axis label. That plots the sample data distribution. So we can take the same function and create a new plot for sample means. So this looks more like a normal distribution. So here's your histogram for the single sample. Here's your histogram for the sample means. And that takes care of the wait times in a single sample for 30 patients, and also the distribution of those sample means for 1,000 samples. Ultimately, though, when your code eventually ends up going into production, and the way that Python code is executed is everything runs from the top down. So a lot of times what people do is they run this cell, then they go back, they forget something, they run that cell, or they run the notebook once and then they forget to restart it. So a lot of the stuff gets stuck in memory and you forget what comes first and what comes last. As long as you provide that line one time and you're still executing that same experiment, it'll stick to that seed of 0 because you only set one random seed for this entire notebook. If our random seed is 0, here's the array of our numbers for both. So if you can take a quick snapshot in your mind, remember these numbers 68.94 and 108.547. So if we change this random seed to, let's say, I don't know, 12, watch what happens if I restart and clear outputs, run all. These numbers change. Now it's 89 point something, 75 point something. And if we run it again, and you'll see that that's reproducible. There we go.